start us off on the panel, we've got Max McCarthy with Evonik.
Okay, well, as Sean said, my name is Max McCarthy. I am actually the Northeast Regional Business Manager at Evonik. Our Southeast guy couldn't come here, so any local questions, I'll do my best. A little bit more about myself. I work at Evonik. Evonik is a global specialty chemicals company. We manufacture chemicals of all kinds. I specifically work on silanes. I'm in charge of business in the Northeast, as I said, but before that I worked in the lab as a scientist. I have a degree in chemistry from Penn State, and today we're going to talk about some surface applied corrosion inhibitors. So just a little agenda of what I want to go through today. We're going to start with just the basics. What is an organofunctional silane? Testing procedures for these organofunctional silanes, both in the field and in the lab, followed by a few case studies, and then kind of some new products, trends, and technology that are out there that are pertinent for DOT applications. So, to start, what are organofunctional silanes? I mean, at their most basic, they're a clear liquid that gets applied to the surface of concrete. It's a pretty rudimentary definition of them right there. But to get into some details, what a silane is it's a molecule that has a silicon atom as its center. And then coming off of that, it has alkyl functionality, which provides hydrophobicity, as well as ethoxy functionality, which provides reactivity, which in English means that these are hydrophobic silanes that can make your concrete water repellent, but can also react with the rebar or steel to repassivate steel in corrosive environments. Most of this hydrophobicity comes from this hydrophobicity and this corrosion inhibitor comes from one single silane molecule because the molecule has multiple reaction sites on it. This small molecule can reach down, can penetrate through the concrete, water-thin liquid, lower viscosity than water, so it will penetrate anywhere from a 1/4 inch to an inch into a concrete deck. A visible penetration followed by the inhibitors really getting deeper in there past the point of hydrophobicity to interact with really that top level of rebar, that top mat of rebar in most situations. Like I said, chemically reacts with concrete and steel to make concrete hydrophobic and repassivates. And then organofunctional silane corrosion inhibitors can do everything you expect of a normal silane as well, which is, extend the lifetime of your deck first and foremost, but then also help prevent freeze-thaw damage by not allowing water to enter the concrete, which if you stop water from entering, you'll stop freeze-thaw damage because there will be no expansion of the water when it freezes inside of the concrete. As well as ASR damage, because if you knock out the component of water and you have the reactive alkali groups, the reactive silicas, and in your mix, then you can't form any ASR gel, so it doesn't, you can't get that ASR damage. Again, limitations with all of this. Not saying that you're going to cure every ASR out there, but especially ASR on the surface of a concrete system, they're shown to help. Some other just kind of quick facts about silanes. Organofunctional silanes, especially ones with the low molecular size, like a few manufacturers have quick dry times compared to some kind of traditional silanes. For example, just to put our product out there, dry time of 1 hour, which means that you get to reopen your bridge deck a lot quicker. You have a lot less unhappy customers of people waiting behind the barricade waiting to go on their bridge deck. Happier for everyone, saves time and money from the DOT and the contractors. These are all 100% silane solutions, so there's no worry about water in them freezing or anything, so they can be applied in low temperature conditions. As I said, I'm from the Northeast. We actually have to worry about that. I don't think you guys have too many issues down here with that kind of stuff, but maybe once in a while. Easy surface prep. You need a ICSP 2 to 3, really just a power wash. Make sure you get all the dirt, all the latenance, all the anything that's going to block the pores from accepting the silane. And then you need to allow it to dry afterwards because silanes work by reacting with water. Organofunctional silanes, just like your normal kind of water repellent counterparts, they don't change the surface friction, they don't change the slip resistance once they're dry. It's important to say once they're dry, you shouldn't open the bridge deck until it's dry. And then once they're on. They're compatible with membranes, coatings, overlays. They are hydrophobic, so if you're using a water-based membrane on top of them, the application may be different. You may kind of get some resistance, but the act of, brushing using a roller and rolling on a coating, or even spraying on a coating, will break the surface tension, which therefore will allow the coating to stick to the concrete, as well as the surfactants that are inside of these coatings and membranes, and overlays are never an issue. And then finally, organofunctional silanes are effective in high chloride environments. We have testing that shows effectiveness upwards of 5,500 ppm of chloride at the rebar level, where the silane is still able to penetrate, interact, and repassivate the rebar. So here's just a little image to show, easy application. This isn't really rocket science here. This is kind of our recommended DOT approach for applying the silane, is a spray bar. I'm sure some of you have seen these before. They're pretty much just, a rig with a garden hose and some spray nozzles on the end attached to a pump and a compressor. Most of the manufacturers out there, including ourselves, including our competitors, will loan these out to you. And you combine this with a 1 hour dry time, you really get the turnaround of bridge deck quite quickly, which I'm sure you guys are happy when you don't get as many calls about bridge decks being closed. All right, so that's kind of the basics of what are silanes. So I want to go into some field testing, some lab testing. Really, I don't mean to bore anyone with super crazy in-depth discussions of this. I'd be more than happy to have those discussions if anyone wants to talk afterwards or ask questions, but I'll just kind of go over the basics right here. So field tests for corrosion inhibitors. Again, organofunctional silanes are dual functional. They act as a corrosion inhibitor and a water repellent in one. So I'm not really going to touch on the water repellency test, but more the corrosion inhibition aspects. Again, you want to talk about water repellents, we can talk afterwards as well. But the main field test that is done to determine corrosion activity that's most effective with an organofunctional silane treatment is a Galvopulse linear polarization resistance test. It's a pretty simple test to run. You need to chip to the rebar, hook up the Galvopulse, wet it out so that you get the full circuit. This little piece there connects on, and there's a wet sponge at the bottom. And then that instrument right there is the Galvopulse. And what it does is it can measure the corrosion current that's ongoing in the rebar between the anode and cathode, just off base locations. It can measure the half cell potential. It can measure, and then it can also measure the resistance. So all the electrical properties that you would expect out of really any type of electrical testing. And here's where kind of results you get. Our most useful result is corrosion current. All this data can be converted to, it's presented here in microamps per centimeter squared. That's where the data is going to come from on the Galvopulse, but that can be converted to cross-sectional loss of steel. There's equations out there. You have to factor in environment, type of steel used. So once the testing is done, that can easily be calculated. And really just different categories. These are by ACI, less than 0.5 microamps per centimeter cube. You're in passive conditions, which means that there's no active corrosion going on, or so little that you're not really testing it. Don't have to worry about it. There's not necessarily a time to visible deterioration yet. 0.5 to 5, you have a low corrosion level, and you probably have about 10 years until you're going to start seeing cracks in the deck due to corrosion, or cross-sectional losses, steel, maybe some spalling. It really obviously depends on the job. I don't really need to read through all this. You guys can see all of it. But and finally, all these results can be presented on two-dimensional maps that you can mark. It really just depends how much you want to chip into your deck, how much you want to test the rebar. You do get kind of the map not from the points, but by going across, so you don't have to test every point. But what you see here, and again, this is no empirical testing or anything, but just to give you an idea of what this testing kind of looks like. This was on a bridge deck in New Jersey probably about 10 years ago now. And you can see on the left, that's the before treatment, just marked off a grid, did some testing, and you saw there's some definitely elevated points of corrosion. The scale's kind of hard to see, but it is in micrograms per centimeter cube on the left side, maybe the right side too. Honestly, I can't see that one, but you can see they're well over 100, it's probably in less than. It's probably 100, I think would be 10 micrograms per centimeter cubed in the scale. Yeah, micrograms per year. So that before inhibitor, and then on the right, apply a corrosion inhibitor, and you can see, you know, these products help. They're not going to do everything. You need to take care of your bridges. This isn't a one-step cure-all, but you can definitely see some reduction in corrosion activity. So finally, some real test data. I want to talk about the U.S. Bureau of Reclamation M82 testing protocol. This is a test that was in development for almost 20 years. Came out, I want to say, in the mid-2010s. We'll call it 2012, somewhere around there. And it is just a general test procedure to test any type of corrosion inhibiting concrete repair product. It can be modified many ways to test many different applications. Obviously today I'm going to talk about surface applied corrosion inhibitors, but other people test many other properties here. So the test is very large scale, but simple and effective. So pretty much what it comprises of is 3 large concrete slabs that are poured with reinforcement that is connected to electrical resistance equipment that's connected to an indicator, so you can figure out the current that is going through the rebar to measure corrosion potential, to measure integrated current, and to measure resistance. These slabs, no treatment is applied or anything. These slabs are then ponded with 5% sodium chloride with a salt solution for 14 days on, 14 days off on continuous cycles. So one cycle takes 28 days, about a month, to test. And again, no inhibitors added, nothing like that. Finally, once the test indicates that the rebar is no longer passive in starting to corrode, once there is a current that is measuring above a set amount, then repairs are done to half the slabs. In this case, a surface applied corrosion inhibitor is added, and then you measure the integrated current, the relative humidity, the chlorides, and the half cell potential on both the treated and untreated, and you can compare the differences. So here's some data. You can see cycle 7 in this case is where it reached that. There's 2 different scales here. I'm sorry, it can be a little bit confusing, but on the left, cycle 7 is where it reached that level where repairs were deemed necessary, where corrosion had started. It was at 1700 ppm of chloride. So then half the slabs were sprayed with our corrosion inhibitor, our surface applied corrosion inhibitor. And then the test is continued the same way, 2 weeks on, 2 weeks off of the chloride solution. And you continue to measure the chloride data. As you can see on the control, there's nothing stopping the chlorides from penetrating, so they continue to aggressively get higher concentration towards the rebar. It's not on here, but this depth is at 1.5 inches. And then you can see that even after a corrosion inhibitor is added, that the chlorides do increase. That is mainly just due to the test being at 1.5 inches. You apply a silane to the top, you still have chlorides from the top of the slab down to the 1.5 inches, so they're still going to migrate down, but you can see there's a pretty significant reduction in chlorides. And then on the right, you can see what really matters, the average integrated current. This shows you the corrosion potential of these slabs. So the red one is the control slab, or the control slabs. This test is completed until all the control slabs crack, and then 2 additional cycles of the treated slabs thereafter. So you can see each cycle, it's more of a guessing game, but we say that each cycle represents about a year of a high chloride environment. We like to say a city like Chicago. So this is kind of a simulated 5-year test right here, but you can see there's significant reductions in the integrated current between the control and the treated, which really means that you're going to have a lower corrosion potential. Finally, once the test is completed, like I said, the test is completed. Once the control slabs crack, plus 2 additional cycles on the treated slabs, the slabs are autopsied and the bars are removed. They're measured for the degree of corrosion, the light, moderate, heavy, and then pitting corrosion. are all assigned a value 1 through 5, and then kind of the averages are taken from them. So here's the results that we have with our product. The average visually examined corrosion percent on the top bars. You can see that there's significant reductions throughout, but there is still corrosion in the treated bars. That is because the corrosion has started before the corrosion inhibitor is applied. There's no way to test if you are a corrosion inhibitor yet after it's applied without having corrosion, because you need the corrosion start to inhibit. And then the total crack length is also measured, and again, you can see significant reductions there as well. So finally, I just want to take you through some case studies and leave plenty of time for questions. This is a bridge in New Jersey, Patterson Plank Road. 2 overpasses here are over, I believe that's 95, the Jersey Turnpike. In North Jersey, this was an aging structure. The chlorides at 1.5 inches were 1,500 ppm. There was moderate corrosion evaluated, including several hot spots with, again, using galvo pulse testing. It was calculated that these measured 0.3 millimeters per year of cross-sectional loss, which is significant. So then all the spalls were repaired, and the organofunctional silane was applied at 100 square feet per gallon on the deck. We came by a year later after it was treated, took the corrosion rate again, and this is the back calculated micrometers per year of sectional loss. And you can see between 2008 when it was untreated and 2009 when it was treated, significant reductions in the corrosion rate. Again, these products can be used on more than just bridge decks. We are here today to talk about bridge decks. We're going to focus on them, but this is a parking garage in Pennsylvania. This is an interesting project because we've gone back and reapplied product 3 times now, including this year, pretty much every 10 years since the repairs were originally made in 1996. This is a heavily exposed deck to freezing rain, snow. Spalls and delaminations were throughout on this deck. They were repaired just using normal concrete repair methods, and then the product was applied. The organofunctional silane was applied to all of the exposed concrete. Corrosion testing was performed annually for 11 years on past performance, and this is the data we have. So you can see, again, significant reduction. Simple technology, nothing really too complex to use, but it works because silanes are able to form that chemical bond. They chemically react with both the concrete and the steel. They repassivate the concrete and they repassivate the steel and they make the concrete hydrophobic. So you're addressing the problem and stopping future problems at the same time. And then last one to touch on, case study 3, is the substructure of a bridge in Milwaukee. This is in 2011. Bridge was not in great shape. The untreated corrosion rate was 5 to 10 micrograms per centimeter cubed. Came back 6 years later after application, and you can see there significant reduction. And just a picture and lines. Take what you want from that. So, and then finally, just some other structures that recently have been treated with organofunctional silane corrosion inhibitors. Like I said, I'm from the Northeast, so a little bit of my favor over here. But finally, just some new technologies that are coming around in this space. Traditionally, this has always been solvent-based 100% silane products. I'd say those are still the best case to use in 99% or best product to use in 90% of cases, but there are certainly applications out there where you can't use that. Not so much over here, but if you're involved in other states, then VOC laws sometimes restrict using 100% silane products. So there's water-based solutions that are now able to be made without having to use a high concentration of siloxanes, and then also water-based liquid admixtures, which we just recently launched, and still looking for some demo projects. So if anyone has anything they would like examined, we'd be more than happy to talk about. Yeah, that's it for today. Any questions, I'd be more than happy to address. Yes, sir.
How does the product affect the passivation layer? You mentioned that it dries in an hour. Is it continually diffusing into the steel even after it's dry?
Exactly. So the dry time is 1 hour. That's the reopening time. You're not getting to the rebar in an hour. It normally takes probably around a month and a half to get full penetration. It's going to continue to diffuse through the concrete. You'll have water repellency due to that diffusion in normally around 5 to 7 days, and then the product will continue to diffuse until it gets to the rebar.
Will it be effective on a marine substructure where the columns are already saturated with water?
So no, silanes are not very effective in below grade or in submarine applications because the hydrostatic pressure will be able to break that surface tension that they provide, and then water will just be able to pour in.
I'm going to kind of put you on the spot, so I don't know if you have the answer, but what is the molecular diameter of these products?
That is a good question. I want to say it's between 5 and 10 angstroms, I would say is a good estimate. They're just monomers, simple monomers. If you want to get into a real discussion about the chemistry, we can certainly have that. But yeah, I mean, they're one silicone atom and six chain carbon atom. It's not, or carbon molecule, not very large at all. Much smaller than the pore of a concrete.
Thank you, good answer.
What concentration of the inhibitor you need at the steel surface for it to be effective?
It's very specific on the. So two parts to that answer, I would say. Part one is that the inhibitor is the silane in this case. It's not the same silane as the silanes that are used as water repellents. There's inhibitor functionality to the silane. So it's the concentration of the silane at the rebar. And the passivation layer is only 1 or 2 molecules thick, so not very much concentration at all. You just, they react kind of unimolecular around the steel.
Would you say it's anodic or cathodic inhibitor?
I would say it kind of works on its own mechanism, not so much due to anodic protection or cathodic protection.
You're on a cathodic inhibitor?
Sorry?
It's a cathodic inhibitor?
No, I'd say that it really doesn't fall into either of those categories.
Oh, we'll talk later.
Yeah, okay.
All right. Thanks, Max.
Thanks,
Appreciate it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.